Question 1. It says, let us to collect the definition and several properties of the examples of stochastic process. So we have 7 different processes here. So let's see what can we do. So for the first is Poisson process. For the Poisson process, is defined by following properties. First, the number n t1, t2 of the points ti in the interval t1, t2 of length t equals to t2 minus t1 is a Poisson random variable with parameter lambda t. So we will have this probability that n t1, t2 equals k equals to e minus lambda t, that lambda t k divide k. Yeah, we have this one. And also if the interval t1, t2 and t3, t4 are non-overlapping, then the random variable n t1, t2 and t3, t4 are independent. And also at a time moment t, there is no more than one Poisson point. Using the points ti, we form the stochastic process xt then equals n0t. So we will have this join like this. And yeah, for the other properties that the first order probability minus, we have probability that xt equals k equals to e lambda t tk divide k. And for the main is expectation of xt, right, equals to lambda t. And for the autocorrelation, that r t1, t2 equals to lambda square t1, t2 plus lambda minimum t1, t2. And for the autocovariance, that ct1, t2 equals to lambda square t1, t2 plus lambda minimum t1, t2 minus lambda t1, lambda t2, which is equals to lambda minimum t1, t2. Yeah, this is for the Poisson process. And second is the Poisson increment process, which is defined like yt equals to xt plus epsilon minus xt divide epsilon. And for the first order, we will have a probability that yt equals to n divided epsilon equals to e lambda epsilon n divided. And for the main is lambda. And for the autocorrelation, we have 2 ways. So first, when t1 minus t2 module is larger than epsilon, we will have it equals to lambda square, and otherwise it will equals to lambda square plus lambda epsilon lambda t1 minus t2 epsilon square. Yeah. And the third one is point impulse process, which is defined as zt equals to dxt dy dt. Yeah, for this we don't have probability methods, and for the main is lambda. And for the autocorrelation equals to lambda square plus lambda eta multiple T1 minus T2. And for the covariance, that C T1 T2 equals to lambda eta multiple T1 minus T2. And the fourth one is semi-random telegraphic signal xt. It's defined based on Poisson points again, and the number in T1, T2 of the points Ti in the interval T1, T2 of length T equals to T1 minus T2 is a Poisson random variable with parameter lambda T. Yeah, and for the first order probability masses, we'll have two different, because the first one is probability that xt equals to 1, and the second one is probability that xt equals to minus 1. For the main is expectation of xt equals to e minus 2 lambda t. Yeah. This is what I have, and for the autocorrelation equals to this one. And for the autocovariance equals to this. And the fifth one is random telegraph signal, which is yd equals to axt. And the probability that a equals to 1 and the probability a equals to minus 1 is both 0.5. So for the first order probability masses, we have probability that yd equals to 1 equals to probability yd equals to minus 1 equals 4.5. And for the main is 0. And for the autocorrelation and the autocovariance seem like semi-random, or yeah, it seem like semi-random telegraph signal. The sixth one is random work. So the random work, the main is 0, and the autocorrelation is the minimum of nm multiple r square, and the autocovariance is minimum of nm. It's also minimum of nm and multiple r square. And the seventh one is Wiener process, which is like right like this. And for the first order, we have this. For the main equals to 0, and for the autocorrelation and autocovariance both equals to minimum of T1, T2 multiple A.